right, good morning. We're going to get started. So I was going to open this up to questions, and I already have a question here in the front. He asked if there would be any nomenclature where, so, you know, in saplings sometimes they'll have a problem and they'll put the name of the compound and ask questions about it. I would never do that because we haven't talked about nomenclature. I haven't taught you nomenclature, so, you know, I would not do anything like that. That would be terrible and cruel. So I wouldn't test you on something that I hadn't taught you already. All right, questions on the midterm? Yes?
To what extent do we need to know about?
Say that a little bit louder.
To what extent do we need to know about functional groups?
You need to be able to name functional groups. As far as reactivity of functional group, you should recognize things like pi bonds and lone pairs. But really, we will take the whole year to talk about reactivity of functional groups. Okay, so that's not anything you would worry about right now. We're not in the point where we predict reactivity. Just acid-base reactions would be the only reactivity we talked about. More questions? Yes? You can, if there is a name on the chart in your notes, that's an okay name to use. So if you have an alkyl halide, you could name that. But if it's a bromide, say bromide rather than halide. So if you have an alkyl bromide, you can say alkyl bromide or you can say bromo group. Okay, so anything that's in that chart. That's why I redrew the chart. The chart that's in your book has extra things that I don't want you to name. So yeah, that's why some of those columns are empty. Yes, more questions? Yes? A little louder. There are no calculators allowed, and there are no, so I have more pKa charts if you didn't get them. Do not bring these with you. So what you're going to bring is a pencil and an eraser. Please do not use pen. Please, please, please do not use pen. Okay, yeah. I will give you a abbreviated. I give a little abbreviated one where I leave out the transition metals because we're not using transition metals. So yes, I will have a periodic table. And there's one up here, but you probably can't see it in the back. More questions? Okay, we're going to talk about applications. We're going to finish up chapter 3 today and start chapter 4. I'm not testing you on applications, but hopefully if most of you are bio majors, you should find some of this stuff pretty interesting. But I'm not going to be testing you on it. So we can take our solubility principles and apply to biomolecules. So here's some biomolecules here: uric acid, testosterone, vitamin E. So is testosterone water soluble? So what's our carbon to oxygen or carbon to heteroatom ratio for solubility? Is it like about 5 to 1? We have way more carbons than oxygen. So this is 19 carbons and 2 oxygens. So fat soluble. What about uric acid? It's just littered with oxygens and nitrogens and way more than we have. 5 carbons altogether, and we have many oxygens and nitrogens. And there's 4 nitrogen-hydrogen bonds, so we have a hydrogen bonding that can happen here. So definitely this is going to be water soluble. We did talk about solubility, so I may have a solubility question or two on the test. What about vitamin E? Water soluble or fat soluble? Definitely fat soluble. 29 carbons and 2 oxygens. So fat soluble. All right, so there's some biomolecules. I also want to talk about soap. Soap is an example of a surface active compound, also called a surfactant. Surfactants are molecules with hydrophilic ionic heads. So here's the ionic portion of this molecule, and that's called a head group. So this is an ionic head and a hydrophobic tail. So in order to be a soap, the hydrocarbon chain that's in the tail has to be at least 12 carbons long. So 12 and longer. So it has to be 12. If it's less than 12, then it's not going to behave like a soap. And what a soap does is when you dissolve a soap in water, it makes a micelle. So what happens is that you get spherical droplets having ionic heads on the surface and nonpolar tails packed together in the interior. So again, the 12 is the magic number, 12 and above, you will form a micelle. So here's a representation. So we have the circle is the ionic head group, and then this is the hydrocarbon chain. Again, as long as it's 12, you could form a soap. So the water molecules are going to be on the outside of this. This is a cross section, and so if we sliced a micelle in half, it's actually going to make a complete sphere. So we have water here. We know the polarity of a water molecule, partial negative on the oxygen, partial positive on the hydrogen. So the partial positive hydrogen is going to be towards the ionic head groups. I'm just going to draw a couple of these, but of course this is completely surrounded by water. So again, the polar head groups on the outside. And nonpolar tails on the inside. And so what happens is if you have a solution of water with oil in it, what's going to happen is you add the soap, and the soap is going to form the micelles. And the oil, let me see what's going to maybe show up here. So the grease particle or the oil, that's not showing up at all. It goes in the center here. Does that show up? No. So maybe on it won't show up on mine, but on yours, draw a little zigzaggy grease particle here. It's just beading up here, so it's not working. But the grease particles are going to go on the inside of the micelle, where it's the dissolves like interior is nonpolar, and then the micelle carries the grease particle out, out of the solution. So that's what and so let's label that, even though we can't show it. Grease, nonpolar particles. Trapped in the nonpolar interior. All right, so and I next want to move to talk about structure of the cell membrane, and I just there's definitely some similarities. We have this whole group right here is our polar head group. This whole entire thing. So definitely a larger polar head group. But notice when we have a soap, we have one tail. And when we have a phospholipid, it has two tails. So because of the fact that we have two tails here, when you put this in solution, it can't make a micelle because we've got the two tails. So it won't fit together in that shape. And so what it does instead is it forms a lipid bilayer like that. And that just has to do with the fact that we have one tail here and two tails here. So this is our phospholipid bilayer. Polar heads interact with the polar solvent water, so we have water on the outside here. We have water inside the cell. And then we have this greasy interior here in that lipid bilayer. And in that lipid bilayer, you'll see things like cholesterol, which is also nonpolar. It's going to give this some structure here. A lot of things are in the nonpolar things are going to be in the nonpolar interior. All right, so that's what that looks like. You can take lipid bilayers in the lab and you can manipulate them. It's a really long process. It's a really interesting process that they can do this with. But they manipulate them in the lab to create a liposome. So again, the two tails interfere with this making of micelle, but we can manipulate this. So we have, here's our lipid bilayer here. But we could actually leave a channel on the inside that's a hydrophilic channel on the inside. So these are really great for drug delivery. You can put hydrophobic drugs in this hydrophobic region. And in the middle section here, so sometimes we need to have more than one drug. In the middle section here, we can supply hydrophilic drugs. In fact, they can even trap microcrystalline hydrophilic drugs in the center portion of here. So this is used for drug delivery. So liposomes not naturally occurring, but we've created to have more like a structure of a micelle. Some more applications: transports across the cell membrane. And how are ions transported across the cell membrane? Because we know from this lipid bilayer that we have this hydrophobic portion. And so if we have a polar drug, how are we going to get it across there to the other side? So some ions are transported across the cell membrane with the help of ionophores. So this is an ionophore. Organic molecules that complex cations, they have hydrophobic exterior. So it's not completely hydrophobic, but it's relatively hydrophobic on the outside of this molecule known actin. Relatively hydrophobic exterior. And in the inside, we have a lot of these oxygens that have lone pairs, and they can complex ions. So if we draw all those lone pairs in, you can see that we can complex ions in the center of this molecule. This particular ionophore is produced by Streptomyces. And in this particular ionophore also has a high selectivity for potassium and ammonium ion. So K plus and NH4 plus. It's just the right size. And you can actually make these in the lab and vary the chain length so you can complex different ions. Here's not one that is naturally occurring that's actually made in the lab, and it's called a crown ether. All right, so that is our skeletal structure for a crown ether. Here's the actual three-dimensional space-filling model for the crown ether. And so let's just put a little arrow, so that's what that looks like up here, three-dimensional. And as you can see in the interior here, we have these oxygens, just like we do with the ionophore, the naturally occurring ionophore. And the size of this particular crown ether, there's different sizes. When we make these when we have naturally occurring, we take what nature gives us, but when we make them in the lab, we can vary the length. And so this particular one is perfect for potassium. So potassium goes in the center here. And we have the partially negative charged oxygens, and you can see they're completely lined up to complex this cation. Oh, those don't even show up at all. So partial negatives is what I'm putting on all of those red parts there. So partial negative charges there. All right, so when you use a crown ether, the ether is called the host. The host is the crown ether. I love this terminology. And the cation in the center is the guest. So we have the host, and then we have the guest. So it's kind of like a hotel room. It's just specifically sized just for that potassium ion. So that's the guest. And for this particular one, the cavity diameter is, we'll write it down here. Cavity diameter is 2.6 to 3.2 angstroms, which is the perfect size for potassium, with an ionic diameter of 2.66. So there are other ions that can go in this, but it is perfect for a potassium ion. So what do we do with crown ethers? One of the things that we can do with crown ethers is we can dissolve ionic compounds in nonpolar solvents. So if we have a crown ether, we could say take potassium hydroxide, and we can actually pull apart the potassium and the hydroxide and actually dissolve the salt in a nonpolar solvent like hexane. So really works well. Questions on applications, anybody? Yeah, I'm not going to test you on this. I do want you to recognize solubility, though, to be able to predict solubility. All right, so we kind of skipped around. We're going back to the last page of this chapter. And what we did with the resonance structures and electronegativities is we find out where in the molecule we have places where there's partial positive charge, where we have places where there's partial negative charge. We looked at electrostatic potential maps, which kind of can help us visualize where those spots are. And the reason we do that is because we want to be able to predict reactivity. So if we have electron deficient sites in the molecule, that's where nucleophiles are going to attack. If we have nucleophilic sites in a molecule, that nucleophile is going to attack another molecule that has an electrophilic site. So electron-rich sites react with electron-poor sites. And that pretty much sums up all the reactivity in organic chemistry. So here's some common reactivity that we're going to see coming up. Right now, I'm not asking you to predict reactivity, except for acids and bases. That's it. So this is some reactivity that we're going to see. Electron-rich pi bond, we talked about that already. Attacking electrophiles, that is chapter 10, which is in 51b. So not something we need to worry about now. So alkenes react with electrophiles because they are electron-rich. Alkyl halides mostly react with nucleophiles. And that's because we have electron-deficient carbon. So we already talked about this here, electron-deficient carbon. Electron-rich chlorine, because the chlorine is pulling electron density towards itself. And here's my generic, this is my generic nucleophile. You'll see me use that a lot this year. And here's my generic, E+ is my generic electrophile. All right, so the nucleophile is going to attack the carbon, and we're going to break the carbon-chlorine bond. So that's some common reactivity that we're going to see in chapter 7, which is this quarter. We'll see this reactivity in Chapter 7. So not expected to be able to predict that now, certainly for midterm 1. We haven't talked about it yet, but we will in depth talk about that in Chapter 7. You may ask yourself, well, you know, an alkyl halide, we have electron deficient carbon. Don't we also have electron rich chlorine? Can't that attack another electrophile? And so what we are going to see a little bit of this. It's not very common to see this. We are going to see a little bit of this. But as you can see, if chlorine acts as a nucleophile and attacks an electrophile, we get something that's unstable. And so that's why we don't see that too much. So sometimes reactivity that we might predict doesn't happen because if we draw the product, it's not something that's stable. So this chlorine would have a positive charge, and that's not a stable compound. So this is unstable. And we call this a reactive intermediate. So we will form this in special cases. But we won't see this until Chapter 18, which is in 51B. So this is just to kind of give you an idea of the type of thinking that we do, and what we've done so far has given us a great ability to predict reactivity. All right, that's Chapter 3. Any questions on Chapter 3? So the exam will be from Chapter 1 to Chapter 3, excluding the applications part that we did today, excluding everything we did today. All right, we're ready to talk about alkanes. Alkanes are aliphatic hydrocarbons. Remember what aliphatic means? Not aromatic. Aliphatic means not aromatic. So aliphatic hydrocarbons having only carbon-hydrogen and carbon-carbon sigma bonds. They can be cyclic or acyclic. Cyclic means they're in a ring. Acyclic means they're not in a ring. So acyclic alkanes have the molecular formula CnH2n plus 2, where n is an integer. They are also called saturated hydrocarbons because they have a maximum number of hydrogen atoms per carbon. Cyclic alkanes contain carbon atoms joined into a ring. They have a molecular formula CnH2n. All right, so not H2n plus 2, H2n. Notice 2 less hydrogens than saturated alkanes. Why? Well, let's give an example here. Let's draw a 5-carbon chain. I'm going to draw out all the hydrogens because we're going to be counting them. We're going to draw a 5-carbon chain here. We're going to have it acyclic, and then we're going to have it cyclic. And if we count the carbons, we have 1, 2, 3, 4, 5, C5, H2, 4, 6, 8, 10, 11, 12. H12, which satisfies the equation CnH2n plus 2, where n is 5. So 2 times 5 is 10 plus 2 is 12. So it satisfies that equation. If we go to a ring now, not something we can do directly, but if we have a ring, let's draw all the hydrogens. Notice we have the maximum number of hydrogens per carbon. That means it's a saturated hydrocarbon. Except this one's not saturated because we don't have the maximum number. The maximum would be 12. Let's count how many we have. We have 2 on every carbon, 2, 4, 6, 8, 10. So this is C5H10. So this is the maximum. Therefore, it's saturated. This is not saturated. So, and we use the same terminology when we're talking about fats, saturated fats, unsaturated fats. Saturated fats have the maximum number of hydrogens. on the carbon chain. So unsaturated fats don't have the maximum number. And the reason that we have to drop 2 hydrogens is in order to connect the 2 ends here, we have to move that hydrogen and remove that hydrogen and then just bond the 2 carbons together. If we tried to bond the carbons together with that hydrogen still there, we'd have carbon with 5 bonds. So when we put it into a ring, we add what we call an unsaturation. All right, so let's talk about unbranched alkanes. Alkanes with unbranched carbon chains are also known as normal alkanes or N-alkanes. So you may see that terminology. Here are the first 4 N-alkanes. This is methane, CH4. This is ethane, C2H6. Notice we're adding a carbon each time. This is propane, C3H8. Notice those numbers here, C2H6, that's saturated, C3H8, that's saturated. Butane C4H10, that also satisfies that saturated equation. So these are all saturated. This is an example of a family of compounds known as a homologous series. And in a homologous series, we add 1 carbon each time. So it creates a family of compounds. Each member differs from the next by the addition of 1 methylene group. So a CH2 is called a methylene group. So some new terminology here. The first 12 N-alkanes are listed in the handout essential nomenclature, which is online. So bring it next time. So the very first question we had today is there going to be nomenclature on this exam? The answer is no. Will there be nomenclature on midterm 2? Absolutely yes, because we're going to start talking about nomenclature right now. Nomenclature of alkanes. All right, so this is a handout that you're going to need to know, but not for this midterm. So notice we have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. I want you to know the first 10. That's all you need to know here. Can you mathematically remember?
Meaning, like, if you see hexa, you know, 6, and then you could just figure out how many.
Yeah, exactly. Yeah, yes. Yes. So most of these are not going to be too difficult for you because you have some experience with this. All right, so you know the first 10. All right, we're going to come back to this in just a minute. So here's the essential nomenclature, which is something that you're going to need to know for starting midterm 2. Let's look at the various representation of propane that we've talked about, and one that we haven't talked about. So we have many different ways of representing these compounds. Gchem C3H8, right? They do that a lot. We don't do that very often. So this is the molecular formula. We know about condensed structure. We know about Lewis structure. So Lewis structure, we show all the bonds, lone pairs if there are any. This doesn't have any lone pairs. But we don't have to worry about angles, bond angles. We know we don't have right angles here, so that's okay with the Lewis structure. This is the 3D, or you'll also see it called dash wedge structure. This, of course, is a cross between a condensed and 3D. We do that very often. Condensed and 3D. This is skeletal. This is something new. This is called a Newman projection. we're going to learn about Newman projections in this chapter. So you'll know how to draw a Newman projection after we finish this chapter. This shows something that we call conformation. New word for you. So a lot of new terminology in this chapter. All right, so we have straight chain alkanes. We also have branched alkanes. As the number of carbons in an alkane increase beyond 3, the number of possible structures increase. An alkane with the molecular formula C4H10 has 2 different ways to connect the atoms together. So that's why we don't like to use things like C4H10, because it doesn't give us any information about what the structure is. Okay, C3H8, there's really only one way you can draw that. If you try that, there's only one way you can draw it. But as soon as we bump up to 4, there's now more ways to draw that. So this has 2 ways. We would call this N-butane. N for normal. Or just butane. You can just call it butane. So if you say butane, this is the structure that will come to my mind that you're talking about. We can also have a branch where rather than having a straight chain, we take this carbon here and move it into the middle. And this is called isobutane. So this little structure right here is an isostructural unit. So if we drew this using a skeletal structure, the iso it kind of makes a V. That's the isostructural unit. These are examples of constitutional isomers, which are compounds that have the same molecular formula but different connectivity. Okay, so constitutional isomer, there are 3 constitutional isomers with molecular formula C5. So we had only one way to draw C3, saturated hydrocarbon. We had 2 ways to draw C4. We have 3 ways to draw C5. So as we go up in carbons, we greatly expand the number of things that we can draw. So this would be N-pentane. Or just pentane. If you write pentane, I would give you full credit for that. This has that isostructural unit. See where it makes a V here? So this is isopentane. And this is another structural unit where we make a kind of a cross here. This is a neo. So this is neopentane. All right, so we've seen it. We're getting increasing numbers of structures as we add carbons. When we go up to 6, and I'm not going to draw these for you, nor would I ask you to draw them. 6 carbons would be 5 isomers. And we'll just qualify this, constitutional isomers. 10 has 75 constitutional isomers. And C15 has 4,347 constitutional isomers. So you can see how just writing this as C6H14 is pretty meaningless. It doesn't give us any idea of how to draw that structure. And even worse when you get up to higher numbers. All right, so we're not going to worry about that, and you don't need to memorize those numbers. But we do have many ways that we can draw these things. Carbons in alkanes or other organic compounds can be classified as primary, secondary, and tertiary. So we use the number 1 with a little degree symbol to mean primary. The number 2 with a degree symbol means secondary. Number 3 with the degree symbol is tertiary. So a primary carbon is bonded to one other carbon. A secondary carbon is bonded to 2 other carbons. A tertiary is bonded to 3. And a quaternary carbon is bonded to 4 other carbons. So sometimes you will see, although it's not as common, for quaternary, it would be a 4 with a little symbol there. I don't think it's either in Sapling or in your book where they use that, but only one of the two. So that's not as common. Hydrogens can also be classified as primary, secondary, tertiary. Primary hydrogens are attached to primary carbons. Secondary hydrogens are attached to secondary carbons. Tertiary hydrogens are attached to tertiary carbons. Quaternary hydrogens, there is no such thing, because a quaternary carbon is attached to 4 other carbons, so it doesn't have room for a hydrogen. Okay, so there are no quaternary hydrogens. So let's label these. This right here, what type of carbon is that? It's attached to 2 other carbons, secondary. I'm not going to label all of these. This is a primary carbon. And the hydrogens that are attached to that primary carbon are primary hydrogens. Can you find the quaternary carbon? Carbon that's bonded to 4. Yeah, right here, second from this end here. So that's a quaternary carbon. And we do have a tertiary carbon here. That's this one right here. That's tertiary. And certainly the hydrogen that's attached to the tertiary carbon is a tertiary hydrogen. So a bunch of new terminology in this chapter. Let's talk about alkyl groups, and then we'll go back to our handout of essential nomenclature. Removing a hydrogen from an alkane gives an alkyl group or an alkyl substituent. So that's the terminology that we use. So if we have CH4, that's methane. If we remove a hydrogen from CH4, now we have a methyl group. So this is a methyl group. Ethane, if we remove a hydrogen from ethane, then we have an ethyl group. So this is an ethyl group. There are 2 possible alkyl groups that can be made from 3 carbons. And as you'll see, as we go up in numbers, there's many more different hydrogens that we can remove. So if we turn this into an alkyl group, we've got many different hydrogens to choose from. So 2 possible alkyl groups that can be made from 3 carbons. This is a propyl group. So this comes from propane. So we drop the E of propane and write YL. So that's a propyl group. Notice this iso functionality. This is an iso group. So this is isopropyl. So same isopropyl that you have in isopropyl alcohol. Okay, so that's isopropyl. There are 4 possible alkyl groups that can be made from 3 carbons, and so now we're going to move to back to our essential nomenclature page to take a look at that. All right, so I'm going to so we have over here we have methane. We remove a hydrogen, we get methyl. So the squiggly line here just means that that group is bonded to something else in the molecule. Maybe if this was a halogen like bromide, then it would be methyl bromide. Okay, so the squiggly line just means this is a group attached to some other R group in the molecule or some other functionality. Yeah.
How is the squiggly line distinct from the R group?
Did everybody hear that question? How is the squiggly line distinct from an R group? Well, if I put an R group here, an R group is a hydrocarbon, then it's really not a methyl anymore, right? You see what I mean? Then it's something else. Unless it's on a ring. So if it was attached to a ring, for example, that would be a methyl group attached to that ring. Okay, so when it's by itself attached to something else that's distinct from what it is, yeah. Okay?
It doesn't need to be a halide.
It doesn't need to be a halide. It could be any functional group or a ring, or so any functional group or a ring. So squiggly is kind of a generic way to show that that's a group that's hanging off of something else. So here it's hanging off the ring, or here we could have it like this. CH3OH, that would be methyl alcohol, so, or methanol. Okay, so remove a protein, and so now we get to ones where we can have branches. If we remove a hydrogen on the end, a primary hydrogen, we get a propyl group. From butane, we remove a proton on either end, we get a butyl group. Pentane, we remove a proton from either end, we get a pentyl group. And then hexane, hexyl group. We don't normally go much higher than that, so that's good enough to know that. There are branched substituents that you do need to know. So we've chosen here, these are unbranched alkyl substituents, but we also have branched ones. We saw already isopropyl. This is the abbreviated way we would write this in a condensed form, so that's isopropyl. This is sec-butyl, so we have 1, 2, 3, 4, and we have a branch on the carbon that's attached directly to some other group. All right, so here, this carbon here is attached directly to this carbon here. If we go here to see the difference between sec-butyl and isobutyl, the sec-butyl has this methyl attached on the carbon that's directly attached to some other group, like a halogen. Here the methyl is on the end here, right from the, close to the end. So basically we make a little V here. So here's the isopropyl. Here's isobutyl. We can have isopentyl too. So something like this. You can keep going and adding carbons. So iso is the V is at the end of the chain. So I think of it like a snake's, the tongue of a snake, how it has the forked tongue. And iso means that that branch is at the end of the chain. We could make a really long chain. We could go like this. Okay, so that's 1, 2, 3, 4, 5, 6, 7. So that would be our base is heptane. This would be isoheptyl. Okay, so the iso, the branch is on the end. Sec, the branch is on the carbon that's directly bonded to something else. Okay, so let's draw another one here. So if we had this, same thing, and the branch was here, that would be sec. That would be sec-heptyl. Okay? So that's the difference in where the branch is. 1, 2, 3, 4, 5, 6, 7. This is where it's connected. So that's why I have the little squiggly line. All right, so that's the difference between sec and iso. This is tert-butyl. We use this a lot. So tertiary butyl. So this carbon is bonded to 3 other carbons, so it's a tertiary butyl. So we can write tert-butyl or we can write T-butyl. Tert-butyl or T-butyl. And this is neopentyl, so it's got that neo group that we're talking about. So that's neopentyl. Those are really the only branches that you need to know. Just wanted to make you aware of the difference between the sec and the iso. It's easier to see on longer chains. Questions on essential nomenclature? Anybody? All right. Let's talk about systematic or IUPAC nomenclature. So this is a systematic way of naming compounds. It is very rule-oriented, and basically the idea here is that If I have a compound, I want to name it using something so anybody in the whole world could look at that and be able to draw the compound. So there would be no language barrier, there would be no, anything like that. Anybody in the world would be able to draw that compound because, unless you attach a picture to an email or something like that, you have no way of conveying it. If you were talking to somebody on the phone and you were trying to describe, say, this compound right here, you might have trouble describing that in words that anybody could understand. So we have a systematic way of naming things. We also have some what we call common nomenclature. And there's some common compounds that you're going to need to know, but very few. Very few common compounds. So like things like glucose. I mean, if I say, okay, now draw me glucose, unless you know glucose and have it memorized, you won't be able to draw it. That's a common name. So a systematic name gives you all the rules for drawing it so that you would be able to draw it if you know the rules. Okay? So unbranched chains are named according to the number of carbon atoms that's shown as essential nomenclature. We already talked about that. For alkanes containing branched carbon chains, what we do is we find the longest continuous chain. Longest continuous. And sometimes it'll snake around, all the way here, but you want the longest continuous chain. If two or more chains within a structure have the same length, choose the one with the greatest number of branches. This is your parent chain. All right, so for this particular one, I'm going to circle the parent chain. Notice, I could have gone with this methyl also. I could have circled this and snaked down here. That would be identical, doing either one of those. That's the longest chain, so that's my parent chain. And I have 1, 2, 3, 4, 5, 6 carbons in that chain, so this is going to be hexane as my parent. My parent is hexane. Number the carbons of the parent chain from one end to the other in the direction that gives the first branch the lower number. First branch the lower number. So let's circle that again. I'm going to start at either end. 1, 2, 3, 4, 5, 6. Or I can number starting at the other end. 1, 2, 3, 4, 5, 6. Which numbering, the top or the bottom, gives the first branch the lowest number? If I go this direction, the first branch is at carbon 3. If I go this direction, the first branch is at carbon 2. So this top one is, and if you are not red-green colorblind, it's the green one, okay? But I know probably a bunch of people in this class are red-green colorblind. So it's this one here is the correct one. Okay, so correct. First branch at 2. First branch at carbon 2. Incorrect. First branch at carbon 3. Name each branch substituent and identify the carbon number of the parent chain at which it occurs. If two substituents are on the same carbon atom, use that number twice. When two or more substituents are identical, use a prefix di, tri, tetra, etc. to indicate how many. Alkyl substituents are named by changing the ane ending to -yle. Okay, so I'm going to circle our branches. We have a methyl here, we have a methyl here. And we have, over here, we have an ethyl. Everybody see those branches? So it helps if you circle the parent and then you just see what are the branches hanging off the parent. So we have 3 branches. We have an ethyl at carbon 1, 2, 3. So we have 3-ethyl. So we write 3, we put a little dash, and then we put ethyl. We have a methyl at carbon number 2 and carbon number 4. So we have 2, 4, dash, dimethyl. Those are my branches. And we forgot up here, we didn't write our parent name. Our parent here was hexane. So we've got the parent, we've got the branches, now we have to put that all together in the name. And this sounds a little overboard here, and it kind of is. Construct the name by writing substituents first, followed by the name of the alkane corresponding to the parent chain. That's fine. The substituent groups are listed in alphabetical order. Oh, we're over time here. I'll stop, and we'll do this next time.